Hello, stats friends. So, chapter 9, I'm hoping will tie up some loose ends for us because we just got done talking about confidence intervals for quite a while. And now we're going to go into testing claims and hypothesis testing. So, this first section is all about the basics and the vocabulary associated with significance tests. Um, I hope this clears some things up, but we're going to dive deeper into it when we get to 9.2 with some prime examples of how we use significance testing. So we're going to really dive deep into vocab in this section, so pay careful attention to that. We're going to be stating appropriate hypotheses for significance testing. We're going to interpret what's called a p-value, capital P, notice. We're going to make an appropriate conclusion for the significance test in context, of course, and then start to interpret type 1 and type 2 errors and give in context and give consequences for accepting one of the types of errors. I know, clear as mud. Let's see if we can make it a little clearer. So we're going to start with stating the hypotheses. So confidence intervals are one of two most common methods for statistical inference, and the other one is a significance test. That's going to allow us to weigh the evidence in favor or against a particular claim. So as we start talking about these, I think a really great example that kind of you can pull from your everyday life is a jury verdict of, guilty or not guilty. And we can kind of talk about that in class more about how we can use that context to think about these questions. So a significance test or a hypothesis test is a formal procedure for using observed data to decide between two competing claims, which are called hypotheses. The claims are usually statements about parameters. And that's going to be a big issue when it comes to the AP tests. They're going to have a caution note coming up here pretty soon about making sure we're talking about the right thing when we write down our statistical symbols. There we go. That's the word I'm looking for. So the claim that we weigh evidence against in a significance test is called the null hypothesis. So null meaning sub-zero there. That's no change. The claim that we're trying to find evidence for is called an alternative hypothesis. So if you want to relate it to the jury trial issue, proving that someone is innocent or not, the null hypothesis is that they are innocent, and the alternative is that they are not innocent. If you want to think of, I think I said that backwards. Scrap that thought. Clearly, I haven't been on a jury in a while. All right, guilty and not guilty. There we go. That's what we're trying to prove, guilty or not guilty. So a free throw shooter claims that his long run proportion of made free throws is 80%. So a proportion of 80% for this shooter. That's his claim, at least. But we suspect that he is exaggerating. So the null hypothesis would say that P, the true proportion, is 80%, while the alternative hypothesis states that the true proportion is actually less than 80%. That's what we're claiming. And it says, notice the null hypothesis is typically a no difference statement. So an alternative hypothesis, in this case, that one was one-sided if it only has a greater than or a less than value for the null hypothesis. However, there are things known as two-sided hypotheses, or alternative hypotheses, and that's where they just claim that it's different. So you're going to see a not equal to symbol in those cases. So I'll get through a couple slides here. There we go. So there's an example of what it would look like if it's two-sided here, where it just says the true proportion is not equal to 0.8. It doesn't say one way or the other. Okay, that took me a while to get through, sorry. So here's a pineapple example of a pineapple company, and they're growing pineapples, and they changed, let's see, last year the mean weight of pineapples harvested was 31 ounces. They used a different irrigation system in the field, and now they're wondering if that made a difference. So notice they didn't state whether, the pineapples were larger or smaller. They just want to know if it's a difference. So the null hypothesis would be stating, now something to point out here, they're using mu, not x bar, because this is not a sample. It's, the general parameter mu is equal to 31 ounces. And the alternative hypothesis is that it's the mean is not equal to 31 ounces. Now it does state here where mu is the true mean weight of all pineapples grown in the field this year. So we're going to show you later about how we use hypothesis testing to make these claims, but right now we're just setting up the vocabulary. There's that caution I was looking for. The hypotheses should express the belief or suspicion we have before we see the data. That's really important if you ever end up using this in real life. This kind of feels fantastical right now because we just kind of throw data at you, but that's not how the real world works. And it doesn't make a lot of sense from the book when we're looking at a problem and we state the hypotheses and we already have all the statistics that we're supposed to work with. Like, that's not how life works. So I know it's a little weird. Um, but anyways, you should state the hypotheses first. And the hypotheses should always refer to a population and not the sample, because that's the whole point of it. We're trying to extrapolate this out to the population. So be sure to state the null and alternative hypotheses in terms of population parameters. It's never correct to write hypotheses about sample statistics. So we don't ever want to see hypotheses with p hat or x bar. Those would be your sample statistics. No, 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 you can't use hypothesis testing. You can't set up your hypotheses with sample statistics. Oh, that's a lot of word. Okay. So here's what they want from us. State appropriate hypotheses for performing a significance test, and then be sure to define the parameter of interest. So I want you to pause the video and read over these carefully, stating what you think the null and alternative hypotheses are. Try to get the correct notation down, and don't forget to state the parameter of interest itself. So here comes some answers. The first one is about sleep study that says 85% of teens are getting too little sleep. Jamie wonders whether this result will hold true at her high school. So she does a simple random sample of 100 students and finds that 75 of those 100 students are getting less than the recommended amount of sleep. So as far as null and alternative hypotheses, you have to remember, like, what exactly were we trying to ask about. And the null hypothesis was that the true proportion of students at the high school was 0.85. And then the alternative was just that it was different than 0.85. This is what we would consider a two-sided hypothesis test. I know a lot of kids would get tricked by this, getting less than the recommended amount of sleep. They're not measuring the amount of sleep in these statistics here, the 75 out of 100. It's the number of students and the proportion of students. So that's why they went with this not equal to 0.85. Okay, spoiler alert on number 2, though. As part of its marketing campaign, the Census Bureau advertised 10 questions, 10 minutes. That's all it takes. And the form will take about 10 minutes to complete, including the time for reviewing the instructions and answers. We suspect that the average time it takes to complete the form may be longer than advertised. So the null hypothesis is that the form does indeed take 10 minutes. Mu is 10 minutes. And the alternative, because we thought it would take more than 10 minutes, would be that mu is greater than 10 minutes. Oops, I forgot to do this on number 1, but mu is the true mean amount of time in minutes that it takes to complete the census form. Now back to Jamie's problem, they used p because it was proportional, right? So proportion of all students at her high school who get less than 8 hours of sleep at night. Fun times. All right, so we haven't talked much about this other than in the introduction, but they're going to throw this thing at you. It's called a p-value. Not to be confused with p hat or lowercase p proportion. This is different. It's a capital P, and it refers to a probability of sorts. So we'll talk more about this later, but for now, a player who claimed 80% of his free throws were made actually only made 64%. So in a random sample of his free throws, 50 free throws, he was actually shooting at 64%. So we're wondering, this is evidence against the null hypothesis that he is a 80% free throw shooter. And it's in favor of our alternative hypothesis that it was less than 0.8 because 64 is less than 80. But is it convincing evidence? That's the trick. And that's where the p-value is going to come into play. So if we look at, we've seen these before, right? This is the simple random sample or simulation. It was a real world simulation here actually, but they dot plotted everything here. Actually, you know what? I think this is just a simulation. Now that I look at it again, there's 400 sets of 50 shots. Yes, I'm sorry, this is not real world data. Read it, Bruzo. This is a simulation of someone who was 80% shooter. This is what would happen if we let them shoot 50 shots in a row and then we plotted each of those data. So the 0.64 or lower only happened 3 out of the 400 times that they ran this simulation. So 3 out of 400. Think about that, guys. Think about what percentage that is. And try to relate this to something we've done before in stats. We know on these weird simulation dot plots that, the smaller out, the smaller the percentage, the more unlikely the I don't want to use the word claim, but the more unlikely the event is. So we have to think about what that means in context of this problem. So I'm going to keep reading here. It says, in other words, how likely is it for an 80% shooter to make 64% or less when taking a random sample of 50 attempts? Well, not very likely is the answer, because if we do the math, we find out 3 out of 400 is like not even 1%. Super duper duper tiny percentage. So what we just calculated was a p-value. The p-value tests the probability of getting evidence for the alternative hypothesis as strong or stronger than the observed evidence when the null hypothesis is true. That is a really confusing statement, or at least a definition of p-value. When we start using the p-values, it'll make a little more sense, but for now, just highlight it in the notes. We'll come back to this. So a p-value calculated at 0.0075, that tells us, oh, we're not going to worry about calculation yet. We're just going to interpret it. So here we go. We didn't calculate it. Or sorry, we didn't interpret it. Let's come back to this. I think they come back. If I remember correctly, we come back to this free throw shooter idea in a minute. I don't want to spill the beans again. All right. So here we are. Calcium. They're claiming, the National Institute of Health, that our teenagers are not getting the appropriate amount of calcium in their diet. So they recommend 1,300 milligrams per day for teenagers, and the NIH is concerned that teenagers are not getting enough calcium on average. Is this true? So the null hypothesis would be that the true mean of daily calcium intake in a population of teenagers is 1,300, and the alternative hypothesis is that it's actually less than 1,300. So they ended up sampling 20 teens. That's not a very big number. We'll get to that later. 20 teens to record their food and drink consumption for one day. The researchers then compute the calcium intake for each student, and here's the statistics. So the average was 1,198 milligrams. So that right there gives us evidence towards the alternative hypothesis, because 1198 is less than 1,300. And then there's the standard deviation. But do we have convincing evidence would be the issue. So explain what it would mean for the null hypothesis to be true in this setting. So, oh, by the way, they did tell us the p-value is 14% or so. We'll circle back to that in a minute. So explain what it would mean for the null hypothesis to be true in this setting. So if the null hypothesis was true, that means the mean daily calcium intake in the population of all teenagers is 1,300 milligrams, like they're supposed to be. Now they want us to interpret the p-value. So this is where, remember, they said the p-value was 0.1404. So we have to kind of interpret what that means for this context. And that's a lot of stuff to write down. Assuming that the mean daily calcium intake in the teen population is 1,300 milligrams, there's a 14% probability of getting a sample mean of 1198 milligrams or less just by chance in a random sample of 20 teens. So think about how we can kind of dissect this and make it into a template. So assuming that the null hypothesis is true is how they started this. There's a p-value probability of getting a sample mean of, here's the X bar, here's the average they got, or less, just by chance in a random sample of 20 teens. Okay. Now, I don't think they're going to ask us to take this further as to whether to determine or not if this is convincing evidence or not. That'll come later, I guess. We're going to move on for a moment. We make a decision based on the strength of the evidence in favor of the alternative hypothesis and against the null hypothesis as measured by the p-value. So here we go. If the observed result is unlikely to occur by chance alone, when the null hypothesis is true, we will reject the null hypothesis. So the fabulous Mr. Dredge, when he taught me stats, would always have us shout, if p is small, reject the null. I know it doesn't quite rhyme, but it works. Okay, it's many, many years later and it's still stuck with me. So if you have a very small p-value, and how small we'll talk later, but a small p-value means that you have enough evidence to reject the null hypothesis. Okay. Now the opposite would be true. If the observed result is not unlikely to occur by chance alone, it's a really weird way of saying likely to occur by chance alone. So if you have a large p-value, that means you fail to reject the null. There's a word of warning coming up here, I'm sure. Fail to reject the null hypothesis does not mean that you accept anything. We'll come to that in a minute. So if the p is small, reject the null. And if the p is large, you just fail to reject the null. Okay. And there is not convincing evidence for the alternative hypothesis. It's all about convincing evidence. So to answer your undoubted question here about, well, how small is small? So in chapter 4, we kept throwing out that 5% thing when we did those simulations for our experiments. We were like, 5%, that's the magic number, 5%. Well, that's a very accepted data value for significance. 5% is something we use a lot in stats, and if you take an AP Bio class and Psych class, 5% is kind of the accepted one that they use as well. So we're going to view anything less than 5% as small. But we're going to find out in a moment that there's times where we want an even smaller p-value or possibly a larger p-value, determining like what we're trying to figure out and what kind of error, sorry to foreshadow, but what error we're willing to accept. So a significance level, and that's an alpha, not an A, it's an alpha, is the value at which we use a boundary for deciding whether an observed result is unlikely to happen by chance alone, when the null hypothesis is true. So before we start our data collection even, you should, as a good experimenter, set up a significance level that you're hoping to work with. So, at the, and they're going to state it at the alpha equals blank level. And we did see this with confidence intervals. I know we use different wording, but it was the same idea. So the p-value is less than A. We say that the result is statistically significant. I hope that doesn't give you nightmares at the alpha equals blank level. So alpha should be stated before the data are produced. We're going to show you later about tricks we can do to change the power of a test or avoid certain types of errors, and some of it includes changing your alpha level, your significance level. That's not really what you're supposed to do with data. It's just kind of what we do to manipulate the data when it doesn't work for our scenario. Talk more about that in the future. Batteries. All right, a company has developed new AAA batteries that's supposed to last longer than the regular AAA batteries. However, these new batteries are more expensive to produce, so the company would like to be convinced that they do really last longer. Based on years of experience, the company knows that its regular AAA batteries last for 30 hours of continuous use on average. The company selects a simple random sample of 15 deluxe AAA batteries and uses them continuously until they are completely drained. The sample mean lifetime is X bar 33.93 hours. A significance test is performed using the hypotheses. So the null hypothesis is that the mean is still 30. And the alternative hypothesis is that it's greater than 30. And we do see some evidence up here where the sample mean was greater than 30, so that's promising. If for some reason you already found out that your your alternative hypothesis and your statistics that you get from your sampling are already conflicting, then that probably means you set up your alternative hypothesis wrong. Or maybe you did bad sampling. That's also an option, I guess. Or maybe it's just a bad claim. I don't know. All right, so where mu is the true mean lifetime in hours of those AAA batteries. So the resulting p-value, they already did the math for you, don't get hung up on that yet, is 0.0717. What conclusions would you make at the 5% significance level? So before they started this data analysis, they said, we need convincing evidence and we won't be convinced unless it's at the 5% level. So here's what it means. Because the p-value is greater than the significance level, we fail to reject the null. So in other words, your p-value was not small enough. Remember, the p is small, reject the null? Well, 7% is not smaller than the 5% boundary that they set up for us. So we don't have convincing evidence that the true mean lifetime of the company's batteries is greater than 30 hours. So notice the phrasing there. We reject the null hypothesis. We fail to reject the null hypothesis. It doesn't mean anything other than that. Guys, caution, we do not accept the null hypothesis or conclude that it is true. All we can say is we fail to reject the null hypothesis. There is not convincing evidence, yada, yada, blah, blah. All right, exam tip. We recommend the following two-sentence structure. from the example when writing conclusion for a significance test. So the first sentence should give a decision about the null hypothesis, so whether you fail to reject or reject the null hypothesis, based on an explicit comparison of the p-value to a stated significance level. Okay. And then the second sentence should provide a statement about whether or not there is convincing evidence for the alternative hypothesis in the context of the problem. I feel a poster coming our way, don't you? All right, this is, well, they wanted me to do this lesson in 2 days. I'm going to be honest, guys. I don't know that I got through all that in 1 day in class, but girl can dream. This definitely would be the second day of class. So if you are running out of steam and you think you only missed the first day, you can stop now. But we're going to talk about type 1 and type 2 errors. So this is, I'm going to be honest, not a friendly thing for my dyslexic brain. So we're going to do a lot of practice with this. There is a cute little matrix coming up in a moment that will look kind of familiar to you from other matrices that we've seen before for making conclusions. And as we've seen in stats, so many things are related to one another. So if you think it looks familiar, it probably does. So a type 1 error would occur if we reject the null hypothesis, but it's actually true. Okay. So a type 1 error means the null hypothesis is actually correct, but for some reason we rejected it. And that's just, the way the stats happens. So there is a probability of that type of error occurring. A type 2 error would occur if we didn't reject the null hypothesis when the alternative is true. Okay. So basically we would have done the math, yada, yada, blah, blah, here's a p-value, and said that we failed to reject the null hypothesis, but actually the alternative was true. Man, that's not any clearer. I literally just restated the same thing I said. So what we need, I think, here are some concrete contextual examples. They're coming up, don't worry. So that is, the test does not find convincing evidence that the alternative hypothesis is true when it really is. All right, so I don't know if this matrix makes life any clearer, but a type 1 error is when we reject the null hypothesis, but whoopsies, it's actually true. A type 2 error is where we say, I failed to reject the null hypothesis, but actually we should have, because the alternative hypothesis is actually true in real life. So depending on the context of the problem, sometimes a type 1 error is more impactful than a type 2 error. And this really has to do with, not math so much as the context of the problem. So here we have potato chips. They're producing potato chips and they get a shipment of potatoes that must meet a certain quality of standard. So the producer determines that more than 8% potatoes in the shipment have blemishes, then the truck's going to be sent away and they'll get a new load of potatoes from the supplier. Otherwise, the entire truckload will be used to make potato chips. So I don't know if you ever opened a bag of potato chips that looked like they're very spotty and almost like burnt in places. Well, those are actually from blemishes in the potato chips themselves, or brown spots and whatnot. So to make the decision, the supervisor will inspect a random sample of 500 potatoes from the shipment, and the producer will use a significance level of 5%. So the null hypothesis is that the proportion is 8%. And the alternative hypothesis is that the true proportion of potatoes is greater than 8%, meaning more than 8% of them have blemishes. So they want us to describe what a type 1 error is and what a type 2 error is, and then talk about, what does that mean in real life? Like which one's more regretful? So a type 1 error, remember, is where we reject the null hypothesis, but it's actually true. So in a type 1 error here for the potato producer, chip producer, they would find convincing evidence that more than 8% of the potatoes in the shipment have blemishes, but actually it's only 8%. So in real life, what would have happened is they would have got all mad and said, oh, these potatoes are terrible. And they would have sent the shipment back. The truckload would have been taken away. They would have brought back a whole new truckload. So you would have wasted supplies, money, time, and the supplier themselves is probably going to be a little feisty because you sent them away and actually their potatoes were good enough. So that's the issue with making a type 1 error in this context. Now, a type 2 error would be kind of the opposite of that, if you want to think of it this way. So we didn't find convincing evidence that more than 8% have blemishes, but actually that's true. So we should have somehow magically figured out more than 8% of the potatoes were nasty. But we didn't, so we kept all the potatoes. So we kept those potatoes, made a whole bunch of potato chips with more nasty potatoes than we should have, and all of our customers are mad now, and that led to, mean Facebook comments and a decrease in sales probably. So which one is more costly? I guess that depends on who you are. If I was the supplier, I would probably be very mad about a type 1 error occurring, and maybe that drives my prices up, which does affect my customer in the long run. But if I was the potato chip producer, I probably would be more salty, no pun intended, about a type 2 error because that means I'm making nasty potato chips and nobody's happy. All right, so the most common significance levels are 5, 1, and 10%. I have a theory it's because it's easy math to do if you were hand calculating things, but whatever. Which one of these is the best choice for a significance test? That depends on whether you would rather have a type 1 or type 2 error. So which one would be more harmful to your cause? So here's the idea. A type 1 error probability, the probability of making a type 1 error is equal to the alpha level. So if a type 1 error is really scary to you, like, oh my gosh, I don't want to have a type 1 error, then you need a small significance level. You need like a 1%. You don't want a 10%, okay? So a type 1 error, if you want to lower that probability, you need to lower your significance level. So we can decrease the probability of making a type 1 error in a significance test by using a smaller significance level. But there's a trade-off. So the probability of a type 1 error and a type 2 error, if one increases, the other will decrease. So if you wanted to, and vice versa. So if you tried to decrease the probability of a type 1 error, that means you are going to increase the probability of a type 2 error. So we got to be careful about that. There must be a happy medium, right? Sometimes. All right. If we make it more difficult to reject the null hypothesis by decreasing alpha, we actually increase the probability that you're not going to find convincing evidence to reject the null hypothesis. I can't read. Find convincing evidence for the alternative hypothesis when it's true. So that's what that blue box is saying. If you decrease the significance level in order to decrease the probability of a type 1 error, you're actually going to increase the probability here of making a type 2 error because it's going to be harder for you to find evidence that's convincing. Okay, here we go. That is a lot of data, but it's about fast food, so I love it. All right, so we have a drive-through issue, and if the customers have to wait longer than 2 minutes to receive their food after placing an order, apparently that's the cutoff for mad customers. So based on store records, the proportion who had to wait longer than 2 minutes was 0.63, and then notice lowercase p, that is the true proportion. To reduce this proportion, the manager assigns an additional employee to drive-through orders, and during the next month, they collect data, random sample of 250 drive-through times, and finds that the proportion of the sample is 0.576. So, I'm looking here and I'm saying, oh, okay, I do have evidence that the proportion was less than 0.63, but is it significant? So they're going to perform the significance test on the following hypotheses at the 10% significance level. So there's the hypotheses. The null is that the proportion is still 0.63, and the alternative is that it has been lowered less than 0.63, where p, lowercase p, is the true proportion of drive-through customers who have to wait longer than the 2 minutes to receive their food. So our first issue is to describe a type 1, type 2 error, and then talk about which error is more serious. And then based on the answer for number 2, are we happy with a significance level of 10%? And then here's the p-value, interpret the p-value. So pause the video, write down some answers. I'm about to spoil everything for you. All right, so we got our hypotheses. Let's talk about a type 1 error. So a type 1 error would be where the manager finds convincing evidence that less than 63% of the drive-through wait times are longer than 2 minutes, but actually it's 0.63. So remember, a type 1 error is where we reject the null in favor of the alternative, but actually the null was true. So a type 2 error would be the opposite of that, where we don't find convincing evidence that it is less than 0.63, when the true proportion is really less than 0.63. So that leads us into number 2 as far as like which one is worse. So a type 1 error makes the manager think that they've improved things, right? They think, oh, well, we just found convincing evidence that our proportion is less than 0.63. Significant evidence that it's less than 0.63. But actually, it's not. Your customers are still waiting as long as they always were, and you gave that extra worker to the drive-through line, so you're paying an extra person technically, and you're taking away from somewhere else in the restaurant. So you're working off of a type 1 error in that case, and that's a pretty bad issue. And they're claiming in number 2's answer that a type 1 error would be more serious because the manager believes the additional employee reduced the proportion when in fact it had no difference at all. Now let's kind of dissect a type 2 error for a moment. The manager does not find convincing evidence that the wait times are longer than that less than 63% of the wait times are longer than 2 minutes. But actually, in reality, it is less than 0.63. So I guess, what does the manager do with that information? Maybe he ends up pulling that extra worker. I think you could make a cause for saying a type 2 error is also a bad idea. I don't know about which one's more serious in this case, because if he pulls that extra drive-through worker and then the proportions and the wait times, the proportion of customers with the wait times more than 2 minutes ends up going up, you're going to have mad customers. So I guess they're correct in saying type 1 error is more serious, but you could argue the other point, I think. Now, because of your answer on number 2, where you said a type 1 error is more serious in theory, that means the only way to fix that is to decrease your significance level. So if he went with I shouldn't say the only way, but the only way we know now is to decrease your significance level. So if he went with an alpha, a significance level of 10%, you can lower that by quite a bit. If that's the error you want to avoid, then lower it to 1%, or at least 5%. So keep reading here. It talks then, see, I didn't bump down. Here's number 4. It says, assuming that the true proportion of all drive-through customers who have to wait longer than 2 minutes to receive food after placing an order is 0.63. So remember how we do this. We're assuming that the null hypothesis is true. There is here's the p-value, 0.0385 probability of getting a sample proportion of, and this was the statistic, 0.576, that was the mean, right? Or I should say p-hat, or less, who have to wait longer than 2 minutes just by chance in a random sample of 250 drive-through customers. So just to kind of hit home what this p-value interpretation looks like, you assume the null hypothesis is true. With the context, so watch out, there's a lot of context there. There is here's the p-value, probability of getting a sample proportion of, here's the statistic, or less, who have to wait longer than 2 minutes just by chance in a random sample of blah, 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 blah. Again, I feel like we need a poster in our lives for that one. That one takes a while to get used to. Oh my goodness, I'm so glad we're done with that lesson. I feel like we have so many loose ends to tie up, and I promise they will be tied up, but like in the next 2 lessons. It's one of those topics you just have to kind of hit and hit again. All right, we'll get there. I promise.